we can ignore this. Okay, now our Atwood machine experiment, I haven't seen all the lab reports, I've just glanced at them, but they should show from your data within experimental uncertainty, and there's a fair amount of experimental uncertainty, since we were timing by a pendulum regulated 1, 2, 3, 4 count. Okay, so that's not an overly accurate result, and often our time intervals were just a few counts, so we don't really know where a count might have fallen, say between 2 counts and 3 counts. That introduces a lot of uncertainty into our experimental results. Clearly we can do the experiment with much greater accuracy, and we've made time observations with much greater accuracy, but this was convenient and quick. So we were able to study a lot of systems without having to take a huge amount of data or take data in a slow manner. Okay, anyhow, we should show, though, within reasonable uncertainty, that acceleration versus the total number of clips that have been transferred is linear. Also, that the slope of a acceleration versus n graph, where n stands for the total number of clips that have been transferred. And remember, we start with all the clips on one side, with an equal number of clips on both sides of the pulley, and some mass in addition to the clips that's the same on both sides of the pulley. So n is the number of clips that have been transferred since we had equal masses on both sides. In any case, that slope should prove to be inversely proportional to the mass of the system. Now, one system had twice the mass of another, and another system had twice the mass of that one. So we're going to get pretty good results here. And we should establish these things within some level of plausibility. And you can take my word for it. Don't know that we'll have time to do the experiment, but you can take my word for it that when this is done with greater precision, with much more sophisticated equipment and measuring devices, and we can do it in a much more sophisticated way. We've got the smart pulley. We can get all kinds of neat data, but that's kind of a black box until we have done it by our own count. Okay, in any case, when the experiment is done with much greater precision, these two things are well corroborated. Okay, now, that's what our Atwood shows. Now we observe that the net force on the system is double the weight of the transferred clips, because every clip we transfer increases the mass on this side and decreases the mass on this side, with a net change in the net force that's equal to 2 times the weight of a clip. Okay, so the acceleration appears to be proportional to the net force because of this. Acceleration is proportional to the transferred number of clips. The net force is double the weight of the transferred clips, and so forth. Also, for given n, the acceleration is inversely proportional to the mass, and that comes from the slope of the A versus n graph and its inverse proportionality to the mass of the system. Now, I don't expect that people have a really good command of proportionality. We have to address it, but we can get the idea, and I'll try to mention just how that works out. Okay, so it follows that for appropriate units, the net force turns out to be the product of the mass and the acceleration. Now, the way we've stated it here, we would draw the conclusion in a little different manner. We would say that the net force is proportional to the acceleration, and the acceleration is proportional to the reciprocal of the mass. Not doing my proportionality signs, the board's a little rough, no excuse. From these two things, we would conclude that the acceleration is proportional to the net force divided by the mass, so that the net force would be proportional to the product of the mass and the acceleration. For appropriate units, we can say that the net force is equal to the product of the mass and the acceleration. And that happens just provided the unit of the net force is equal to the product of the unit of the mass and the unit of the acceleration. Then your proportionality constant is 1, and you have this equality. So, from this reasoning, which actually leads to this, which leads to this, we can use the fact that acceleration then, with our choice of units, is equal to net force divided by mass. And from this, we conclude from the equations of uniformly accelerated motion, just asking ourselves, by how much does the quantity 1/2 mv squared change when you exert a given net force through a given displacement? We conclude that the F net dot delta S product, when you just think of net force times displacement right now, but it really is a dot product, as we'll see later. You don't have to worry about what a dot product is if you don't know. It's a fairly simple concept. That is equal to the change in what we call kinetic energy, where kinetic energy is 1/2 mv squared. Now, in class and in the notes I'm going to go over next, we work out the details of this, but this is the overview. And you should understand this overview, and from this understanding, ideally, you would be able to derive everything. You'd be able to prove this based on this, at least for the case where the net force is constant. And then you could actually use calculus with integration and so forth to show it even if the net force isn't constant. It would be the integral of the net force times the displacement, or change of position. And we'll talk about that, but we don't need to worry about it right now. This is the overview and the scheme of our connection between work and energy, because this is work. This is the work done by the net force as you go through the displacement. And this, of course, is the change in kinetic energy, which is the change in 1/2 mv squared. And if mass is constant, this is just equal to 1/2, well, yeah, we can say it. 1/2 times the mass times the change in the squared velocity. It's not the change in the velocity squared, it's the change in the squared velocity. Now, just theoretically, we need to actually correct our data here for friction. Our data here won't give us perfect results. And the reason for that is because of the presence of friction, you have to transfer a little bit of mass before anything begins to accelerate. Friction will just hold it there until you get enough difference in the masses of the two sides to begin accelerating anything, so that our graph actually looks something like this. It has an intercept here that corresponds to the minimum number of clips, or the minimum fraction of a clip, as it would be in this case, in most cases, that are required to give you any acceleration at all. Whereas the proportionalities that we're claiming over here, a linear proportionality implies a straight line graph through the origin. Okay? It's not like this. So what happens is you have to kind of figure out where the intercept is here, and then move your acceleration axis over in order to get the proportionalities that we're talking about. Now, I'm not going to go into detail on that yet, but we're going to develop that sort of technique in lab. So we have here two very powerful relationships. First of all, the net force is equal to the product of mass and acceleration, and of course this gives you a triangle. You got F net, M, and A, in the sense of the flow diagram, where If you know any two of these, you know the third. And it's obvious from the equation that it's very easy to find that. Mass would be net force divided by acceleration. Acceleration is net force divided by mass. Okay, well, we're going to see the details.